Okay, how would I explain calculus to a sixth grader? So here we have a little question here. Is this sixth grade math? And what we're looking at right here is calculus. And of course, the answer is no, we don't learn calculus in sixth grade. However, the concepts we've already learned in the sixth grade are really enough by the time we've gotten to the sixth grade, the concepts we've learned about mathematics is enough to really understand the essence of calculus and the kind of problems it can help us solve. So that's going to be the objective of this video is really kind of demystify calculus such that anyone can like appreciate the value of it. All right. So, most people, and I can understand, they'll look at, something like this and it just looks so scary. Like, oh my goodness, I'll never understand that. I don't have no idea what it does for us. Well, if you just stick with me through this video, you'll have a nice appreciation for calculus. Okay, so before we get going, let me go ahead and introduce myself. My name is John. I'm the founder of TabletClass Math. I'm also a middle and high school math teacher. So I certainly understand what is taught at the sixth grade level. And over many years, I've constructed full comprehensive online math courses. So if you just need help with math or you need to take a complete math course, I'm going to leave a link to my math help program in the description of this video. Also, if you're in need of some math notes, you'll find links to various math notes in the description as well or underneath this video, I believe. Okay, so with that being said, let's go ahead and get to this topic of calculus, right, and demystify it. All right, so let's start here. And I got some shapes, right? I got a circle, I got a rectangle, and a triangle. And I said, okay, let's find the area. Okay, how can I find the area of these shapes? And by the sixth grade, all sixth graders, and probably even earlier than that, maybe, it all depends, could find the area, or certainly understand the concept of the area of a figure, right? So, yeah, you might be out there, okay, well, I could find the area of a circle by using this formula, pi r squared, right? So the r is the radius, it's the distance from the center to the edge, but if I knew this information, I could plug it into this formula and I could find the area. Okay, you're like, oh, all right, yeah, I remember that. And here I have a rectangle, this is the length and this is the width. So how could I find the area of this guy? Well, again, I can use this formula, area equals length times width. Right? You're like, oh, yep, I remember that. And here I have a triangle. You're saying, oh, the area of a triangle is 1/2 base times height. So this would be like the height right here, and this would be the base. So I could find the area of a circle, a rectangle, or triangle, not a problem, right? So what's the secret though? The secret is knowing the formula for those respective shapes, okay? All right, that's all fine and dandy, but what happens when we encounter a situation like this? You're like, oh, what's going on here? What if I said find the area of this shape, okay? Now this shape is kind of bounded by this little squiggly curve. It has this little border and this border and this border. So now, what do we even call this shape? It's not a triangle, it's not a rectangle, it's not a circle. Who knows? Maybe we'll call this thing a squiggly. Find the area of a squiggly. And you might be saying, all right, no problem. I know how to find the area of a circle. I know how to find the area of a rectangle and a triangle and a few other things. I just need to know the area of a squiggly. Okay, what's the area or the formula for the area of a squiggly? And I would come back and tell you, I'm sorry, there is no formula. There is no formula. Like we were able to use formulas, those nice formulas I just showed you to find the area of these basic shapes. But what about this crazy little looking figure here? Well, we're going to have to come at this at a different approach. So the first thing that calculus does for us, it allows us to find the precise exact area of crazy shapes. Any shape that you want, you can find the area of it. And this goes for volume as well, right? So if I said find the volume of a cube, all right, so most of you might know how to do that. Or like a cylinder, we also have formulas for that. But what if I had like some crazy looking like weird shape like this? Well, there is no formula. We're going to have to use other mathematics, and that would be calculus, and that's going to be our superhero here in terms of being able to find the area of things like this. Now, how does calculus work? What's the main kind of concept of, in terms of being able to find the area of something like this? Well, here's how it works. So if I said, well, just use what you know. Let's just focus on the rectangle, okay? We know how to find the area of a rectangle. Maybe we could just find a good estimate of this little squiggly shape. So you could say, okay, let me kind of draw one rectangle here, another rectangle like this, and kind of like some other rectangles like so. You can kind of see what I'm doing, right? I can just find the area of this rectangle, this rectangle, this one, this one, this one, and add them all up. And I would have a decent estimate of the area of this little squiggly figure, okay? So calculus is going to be conceptually using the area of these basic shapes, precisely the rectangle, okay? We're going to use the rectangle, but we're going to use it in a little bit different way than this. But the main concept I'm trying to get you to understand is that we can get estimates of the area of anything we want by using things that we do know. Okay, we do know how to find the area of these guys, so I can use little tiny rectangles, little things, or I can use bigger ones, and I could just kind of kind of create that shape or estimate that shape roughly, and then add up the area of all those little rectangles. But we're going to use the rectangles more in this manner, okay? So we're going to kind of do it like this, all right? So we're going to add up rectangles kind of vertically, okay, for the purposes of calculus. All right, so you can see here, these are all rectangles. Right now, I have information down here. I can get these dimensions, and I can get the height, and I can get the width. So all I would have to do, now this is a better estimate than what I just showed you, okay? I would just have to add up this rectangle, this rectangle, this rectangle, that one, all these rectangles. If I add up the area of all the little rectangles, all right, I will get a really good estimation of my little squiggly here. Now this is where calculus is kind of heading here, right? That we're developing, or we're looking at calculus in play. Okay, like, well, so far I'm just seeing these rectangles. Well, calculus in terms of solving the area of these crazy figures is effectively using the concept of all these little tiny rectangles. So my question to you is this: what if I said, hey, good job, you gave me a pretty good estimation of this squiggly here, but I want a more precise answer? And you might be like, oh, you want a better answer than that? That was a lot of work, right? That was like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, whatever, how many little rectangles. So, and you had to add them all up. And you're like, all right, listen, you want a better estimation? Okay, fine. Let's get a better estimation. How could I get a better, more precise, a super precise estimation of the squigglies? Well, you guessed it, we can use skinnier, little, tiny rectangles. Okay? Now, I'm not going to do this whole figure, but you could see here what I'm doing is I'm using real super skinny, thin, little rectangles. Okay, they're still rectangles, and I still know how to find the area of a rectangle. All right, nothing's changed, but now obviously you can see I'm going to have a much better estimation of the area. So I know how to find the area of a rectangle again, right? Remember, it's the length times the width, and I can get all that information here. But it's a lot more work, obviously, right? I'm going to have to add up a whole bunch of skinny little tiny rectangles. But take a look at what's going on. I mean, this is getting pretty nice, right? I mean, like, oh, yeah, this is going to be a pretty good estimate of the area of this squiggly shape, okay? So what's the lesson learned here, right? If I want to get a more accurate area, okay, of a particular shape, I want to use skinnier rectangles, okay? Now, what would be like the ultimate skinniest rectangle? Well, it would be like almost infinitely small, right? Super, super tiny, super skinny. But if I was able to just add up all these little infinite little strips, these little tiny like rectangles underneath this, I would get the precise area of this figure. And this is, ladies and gentlemen, the main concept of one of the biggest problems that calculus solves for us is finding the area underneath these little curves, okay? Something that's bounded like so. And so now when we take a look at this little calculus stuff, right? I'm going to go ahead and say 0 to 10, and you'll see what this means here. Okay, now this is actual calculus symbology. All right, you're like, all right, let's understand this. What is this saying? Well, what this is saying in calculus is the following. This little line right here, this curve, okay, this right here can be described. It can be described. Let me erase this with something called a function. It's just a rule. Okay, it's a mathematical description of this curve. Okay, it says, okay, if you follow this rule, you'll get this curve. So in calculus, what we're trying to do, you see our little squiggly starts from 0 and ends at 10. Okay, so in calculus, I can say to find the area of this squiggly, start from 0, go to 10. Okay, and we're going to be describing, or we're going to want to find the area, or we want to add up all the strips underneath this function, okay, underneath this curve, all right? Don't worry about this little notation. That's something, it's not trivial, but we just have to write this, okay? But this little long thing right here, this is called an integral, all right? And basically, it means sum, okay? And effectively, it means it's telling us add up from 0, start at 0, go all the way to 10, all these little tiny, infinitely tiny rectangles underneath this function. Okay, that is calculus notation. That's what that is saying. And there's another notation that kind of goes along with that. It's called a sigma notation, but I don't want to kind of get into it. But anyways, that's calculus. This is it, okay? Something like this is saying we can go ahead and find the area underneath curves on a graph, right? We just need to know the function, right? We need to know the function, and we need to know where we want to start and where you want to stop. So, for example, if I wanted to find the area between like 5 and 10, okay? So this area right here that I highlighted, so I would just go over here and I would write this differently. Okay, I would put a 5 right here and a 10 right there, and there you go. Now, how we actually calculate this mathematically, that's a little bit more involved, not much more involved, but it's something that you can't handle. If I wanted to make this video a little bit longer, I could teach you how we calculate this, okay? But I just want you to understand the basic concept of calculus, this notation. It solves up finding the area of any crazy shape that you want, okay? So if you change the function, you got a different kind of curve or something like that, or whatever, or something like this, doesn't make a difference. We can find the area of anything we want, area and volume, using calculus, right? And we don't need a formula because obviously we don't have direct formula for things like formulas for things like this. Okay, so that is the first problem calculus solves, is like the area problem. Okay, let's get to the second problem. And by the way, this is called integration using the integral. All right, that little fancy thing. Now, you remember this right here, this little dx. All right, this is going to be the second kind of problem. That is a derivative, okay? So the derivative is a little bit more, I don't want to say difficult to explain, but hopefully this example explains it. All right, so the derivative, dx, all right, over dy, you'll see that symbology in calculus. So there's two main things that calculus helps us solve. So the first one you can kind of think of is the area problem. We use that little integration symbol, a to b, I just showed you. And now the other problem is it's a little bit more sophisticated, right? So this one is going to be dx dy, and you can kind of think of this as instantaneous velocity. Um, Let me explain this to you. It's not that difficult to understand, but let me, I'm kind of rambling here, so let's get to this example, all right? And then you'll understand it better. Okay, so here we have a car. Now the car is accelerating. Okay, this car is taking off. Here's my little car. It's going faster. It's going right. So it starts at 0 miles per hour, and it's going to go increase its speed all the way up to 80 miles an hour. And let's say it does this in 10 seconds. Okay, so this is an accelerating car. Accelerating car. So if I asked you, if I said, all right, from 0 miles an hour, 80 miles an hour, and it does this in 10 seconds, said, how fast is this car going at 3 seconds? Okay. At 3 seconds into its little acceleration, how fast is it going? Okay. So you could say, well, it's at 10 seconds, and you might use the formula rate times time equals distance. But precisely at 3 seconds, if it started at 0, it's obviously, less than 80. You might say, I don't know, maybe at 3 seconds it's going, I don't know, let's say 48 miles per hour. Well, how can we calculate that? If you think about it, the car is continuously increasing its speed. Okay? You can't take the distance it's traveled, right, and then divide it by its speed. Okay, so rate times time equals distance. This speed, okay, that's a fixed velocity. All right. In other words, that's if this car was going 80 miles per hour down the highway. Let's say, you're on the freeway and it's going 80, or the turnpike, whatever it may be located. If it's going 80 miles per hour, all the way down the highway, then it's easy to obviously it's going to be going 80 miles per hour the entire time. But it's easy to calculate, rate and distance problems because the velocity is the same. But when we're accelerating, how fast the car is going in this precise moment in time, that's a whole different ballgame. Okay, we need calculus to be able to answer that question for us. So I might ask you, well, what about 5.12 seconds? Okay, into this car's acceleration, how fast was it going? How fast was it going? Okay, in that precise moment in time. Well, and this is an accelerating car, not a car that's going at a constant speed. So these type of problems, to figure out the answer to these instantaneous problems, that I could get a snapshot of what's going on at that precise moment, requires calculus to be able to answer a question like that. We can't use average speed and time and distance. Okay, that doesn't work in this kind of scenario. Let's see if I can give you another example to maybe make this a little bit better. So let's say I had let's say I'm doing an experiment. Say this is the side of a building, and I drop like a baseball or something, right? And I'm doing it safely. There's no one down here. And when I let go of the baseball, it's at 0 miles per hour. Okay, now what's happening with the baseball? Well, it's picking up speed. It's going faster, faster, faster until it hits the ground, right? Let's say this is 120 feet. And I don't know, maybe the baseball ends up going 120. Let's see something different. Maybe it ends up going, I don't know, 105 miles per hour by the time it hits the ground. Now, and it took, let's say 2 seconds to do that. Okay. So I'm just totally making up numbers here, but just to try to get the idea. So if I let the baseball go, I didn't throw it, just let it go, it's starting to accelerate, right? I'm saying, well, how fast is a baseball going at 0.78 seconds? All right, how fast is it going at this moment in time, this moment in time, this moment in time? Okay, well, again, it's picking up speed, it's accelerating, but I want to know its instantaneous velocity at these little snapshots. This requires calculus, okay? And this requires a concept of something called the derivative, okay? The derivative, in calculus, a derivative looks like that. All right, so calculus solves two big problems for us. All right, it does so much more, obviously, but the two big problems you can think about is instantaneous velocity questions like this. Okay, if something's accelerating, we can use calculus to answer these questions. Right, that's the first thing. The second thing is the area problem. Okay, we can find the area of all kinds of crazy shapes, anything we want, and beyond the area, we can find the area of volume, etc. And of course, this calculus does even more than that. But if you didn't know anything about calculus, okay, and you understand this basic kind of math and the question about the car, then you got a pretty good feel for what the value of calculus does for us. I hope. I don't know where you're at in your math education, but I would certainly encourage anyone out there, everyone out there, to explore calculus. I know a lot of you are like, "Oh, I'm going to avoid it as much as I possibly can." But if you could ever take this class, pressure free, just enjoy the concepts of it. Yeah, there's a lot of challenging things to it. There's a lot of rules and other stuff. I'm not trying to minimize it. I'm not saying it's not a challenging math course, but the beauty of it is that it can solve such just awesome real world problems for us. Okay, so that's it. If you need help with math, more instructional, full help, you know where to go. Just follow those links in the description of this video. Also, if you're new to my YouTube channel, I'm posting stuff all the time, so hopefully you consider subscribing. And of course, if you like this video, please smash that like button. All right, so with that being said, I definitely wish you all the best in your mathematics adventures. Thank you for your time, and have a great day.